Hi, welcome to section 18.2. We're looking at a shift in equilibrium. So this is talking about the idea of the stresses I mentioned in the previous section of how we can shift equilibrium to get more of a complete reaction, forward or reverse, and manipulate it to our liking. Be sure to start off with these intro questions, and let's look into it. So there's three different types of ways we can shift an equilibrium, although some of them are increase or decreases. So changes in pressure. Now pressure only affects things that are going to be reactive or affected by pressure, and these are only gases. Okay, only gases. The process will shift to the side with the lower number of moles on one side if the pressure is increased. So what this does is when we think of pressure, that is an idea of how much force is carried over an area or volume. So if we were to increase the pressure of gases in a container, the easiest way to do it would be to decrease the volume. When you decrease the volume, the pressure goes up. So in looking at the number of moles, on the left side, the total is 4 moles, or 3 plus our 1. On the left side, there'd be 2 moles. So what's happening here is that you need 4 individual molecules on the reactant side to come together in the correct energy and orientation. Just like if you have 4 friends trying to meet up at one place, the likelihood of that occurring is going to be less than 2 people meeting up to have a date or meet up for a movie or something. So if we were to increase the pressure, decrease the volume, the likelihood that these 4 are likely to meet if you put them in a smaller space will increase. On the other hand, the 2 people or 2 molecules colliding is maybe going to increase just a little bit because they are going to be technically more likely to hit each other in a smaller space as they're bouncing around randomly in a box. So what that means overall, the forward reaction rate will increase quite a bit, the reverse reaction rate a little bit, which will be a net gain of pushing it towards the smaller number of molecules, of moles. The true is reverse if we decrease pressure. Decreasing pressure spreads these particles out. Those 2 are still going to be likely to find each other if we're talking about the products, the NH3. On the other hand, those 4 are going to be less likely to occur, and you're going to get this reverse reaction being held true to go towards the larger number of particles. Okay. So this would be the increase and decrease pressure of the system. Now concentration will move towards making the reaction equal again. I like using a seesaw in this idea. So a seesaw, or teeter-totter, if you will, would generally be balanced if things are equal under the reactants and the products. So at equilibrium, things are equal. However, if we increase concentration, let's say I've increased concentration of the reactants, just like if I were to add more reactants, that'll make it skewed to where the reactants are tilting downwards towards the earth, products are now up higher. In order to get that to be equal again, some of the reactants will make products, so I'm shifting the weight in order for it to go back to equilibrium. So this would be called a shift towards the products. It needs to be used up, there's more of it. Remember we talked about increasing reaction rate by increasing concentration, increases the amount of collisions that can take place. So that will increase the reaction rate from the reactants to the products. Likewise, I get the same thing happening if I remove some of the products. If I remove some of the products, I still get the same result. to where there's now less products. I wouldn't say there's more reactants, but because there's less products, because I remove some, the reaction rate back is going to be diminished, while the forward reaction rate is going to continue on at the same process. So the idea is that the overall net change would be a shift from reactants to products. So that's why when we talk about an increase of concentration, will be away from the substance that was just increased, while a decrease will be towards that substance, because now there's needed to produce more of the substance to make up for what was removed. Lastly, we talk about change in temperature, differences in heat. So think of heat as a product or reactant just as you did with concentration. So I'm going to use this one down here below as an example. So if I'm at equilibrium, I would be balanced, nice, even, reactants and products. If I were to increase heat, in this thermochemical equation, heat is a reactant. So that would make as if my teeter-totter had the reactants downward on the ground while products up in the air. And just like the concentration, I've increased my concentration of heat, if I wanted to put it that way, would shift it towards the products because now I have more reactants to react to make more products. Likewise, if I cooled off this, again, my products would go, if I cooled off this, then that would be the reverse, to where now I'd have more reactants and products would be heavy. I should say less reactants and more products. So now the idea is that there'd be more products shifting towards the reactants in order to get me back to my equilibrium position of things being level and equal. I often will model this with a pencil to kind of think of the teeter-totter. So usually during the test I see kids putting their pencil in front of their face and tilting it left and right, and that's perfectly legit and a good thing to do. So again, you could memorize this little sheet, although I think it's much more important in the idea of trying to apply this to random situations of what's actually physically going on by drawing some pictures. You notice that adding a catalyst has no shift, and that's because both reverse and forward reaction rates will equal in decreasing or increasing at the same amount, so there'll be no overall change at all. Alright, I'd like you to take what you've learned and apply it to these different situations. Answer on Edpuzzle what these would be, reactants or products, which way you think it would shift. Answer all of those, and then come back and I'll just give an explanation for each one of these. Alright, I hope you answered those. We'll see how you did. Well, I guess it would tell you how you did, but let's go through the explanation if you got any of them incomplete or wrong. So addition of NH3. So if I added more NH3, that's going to make my products heavy. So thinking of products are going to be heavy, reactants are going to be light. So that means there's going to be a shift from the products to the reactants to make them level again. So that would be shift towards the reactants. Removal of N2. So if I remove N2, N2 goes down, there's less of it, that's going to make my reactants light in the same picture in the corner. Therefore, my products are going to shift towards the reactants in order to remove N2. Increase in pressure. So I have 4 moles on the left, 2 moles on the right. So if I'm increasing pressure, I'm squeezing those 4 tighter together more so than squeezing those 2 together. So this is going to favor the idea of being more towards the products. Decreasing temperature. So decreasing temperature is the idea of decreasing heat. And so that would be almost as removing some of the products, which would give me my teeter-totter to be products up high, reactants are heavier, so to speak. So this will need to shift towards the products in order to relieve that stress of change. Removal of H2, well, I had that same concept for N2, so that's going to also shift towards the reactants, because when I remove N2, that's going to make my reactants lighter, therefore the shift is going to need to go from products to reactants. A decrease in pressure. So if I'm decreasing pressure, that means that's going to have a bigger effect on the ability for these to come together, while these are not going to be affected much at all. So it's going to be the opposite and going to be put in the idea of shifting towards the reactants in this case, the larger number, because it's going to favor those coming together. Addition of a catalyst, no change. No change at all. Okay, none. Increased temperature would be, again, increasing heat, which would make it similar to the model up here in the corner. More products, so it's going to shift towards the reactants in order to do that. You're going to get some practice on this in class. I'd like you to answer these questions before you come in, and come in with any kind of questions that you might have from the video. Hope to see you soon. Bye-bye.